Time to look at scoring metrics, major topic in machine learning. Let's dive right in. Okay, let's start with the concept of a scoring metric. So in machine learning, a scoring metric is the method by which a machine learning model is given a score. There are many different ways to score machine learning models, hence many different scoring metrics. In case you're wondering, metric is an official mathematical term. It's kind of technical, but you can think of it as like a measurement of distance in math. But there are different ways that you can measure distances, so there are different metrics. There's like a Euclidean metric, there's the taxi cab metric, absolute value metric. There are other metrics. Okay, so let's start with regression, in particular R2. The default classification scoring metric in sklearn is called R2. That's what we used when we did model.score with regression. It gave us an R2 score. R2, properly pronounced R squared, because that's what it means, it's R squared is the official statistics term, is a measure of how well the data fits the regression line. 1.0 is perfect. 0.5 indicates half the data is explained by the line, half isn't. And 0 means none of the data is explained by the line. But in addition, you can get negatives. And a negative score means the data runs opposite to the line. It actually does happen surprisingly at times in sklearn. You would think that it shouldn't, never would, but there are some challenging test sets. So let's take a look at an alternative called the root mean squared error. So RMSE, the root mean squared error, is a more common scoring metric for regression. The RMSE is the average distance that each point is from the regression line. Example. Assume the bike rental dataset has an RMSE of 21. Well, what does this mean? On average, the predictions are 21 rentals off from the predictions. So the RMSE has a very clear meaning, which is why it's actually popular for regression. In fact, I would say it is the norm. And note that the tricky piece is that unlike with R squared and unlike with accuracy, lower is better. A root mean squared error of 0 means there is no error. That is perfect, okay? Closer to 0, the better. Therefore, sklearn requires taking the negative square root of the negative mean squared error to get the root mean squared error. It does require an extra line of Python code. And the reason why is because sklearn scoring metrics, by default, the largest is the best. And so by taking the negative, it allows it to fit into the general sklearn scoring metric library. Okay? We'll practice it. You'll get used to it. Now, there are additional regression scoring metrics. I tend not to use any of them, but here they are for sklearn. I suppose that you would want to use some of these in some cases. Note, by the way, you do see a negative root mean squared error on here, but it just says mean squared error. So that's the one we'll be using to get the root mean squared error. You just have to end up taking the negative square root. Okay, now let's turn to classification, and let's start with accuracy. So the default classification scoring metric is called accuracy. Accuracy is the number of correct predictions divided by the number of total predictions, given as accuracy equals correct divided by total. If 81% of predictions are correct, accuracy will be 81%. But imbalanced data poses challenges. In imbalanced data, simply put, accuracy is not good enough. Now, an example will make this clear. So let's say that 1% of stars have detectable exoplanets. It's easy to build a machine learning classifier with 99% accuracy. I should say just a classifier. Simply put, say no stars of exoplanets. If you say no stars of exoplanets, hey, that's going to be 99% accurate, because guess what? You're going to be right 99% of the time. Is it a good scoring metric? No, it's awful because you're not detecting any exoplanets. So the idea here is that when your data is very imbalanced, you can't use accuracy. You need an alternative. So enter the idea of positives and negatives. These are official statistical terms. In machine learning, a positive case is a value of 0 and a negative case is a value of 1. For example, using the exoplanet example, stars with exoplanets are positive. They represent 1% of the data. That's what you're looking for. The true positives are the exoplanet stars that are correctly predicted. This is bolded because it's an official term. Your positives are true. But then you could also have a false positive. You could predict that there's an exoplanet orbiting a star and it's actually not true, so it's an incorrect prediction. So that's a false positive. To continue with the example, stars without exoplanets are negative, and that represents 99% of the data, so most cases. True negatives are stars without exoplanets are correctly predicted, and so no exoplanet, you got it right. But then false negatives is when you're missing the exoplanets. You're predicting that the stars without exoplanets, well, it's incorrectly predicted because you're predicting that they don't have exoplanets when in fact they do. Okay? Now, you don't need to be an expert of positives and negatives and get all this. I'm simply going to show you where some different accuracy scoring metrics come from and why they're important to use for imbalanced data. If any of you are working with imbalanced data, I'm going to invite you to revisit this. You can work with myself or the cohort leads to choose the best scoring metric for your case, okay? It's hard to get on the first time, I think. So the first classification scoring metric that navigates this little positive-negative group is precision. The goal of precision is accuracy of positive predictions. For instance, precision is the true positives divided by the total positives. For example, I should say total positive predictions. What percentage of predicted exoplanets were actually exoplanets? This answers that. For instance, let's say that you predicted, 100 exoplanets, and guess what? 85 were actually exoplanets. Well, then it's 85 out of 100, it's 85%. And this is useful in the scenario if you would want to publicize verification of exoplanets. So a high precision would be, you're very likely that it's correct. You can work with scoring metrics to adjust the models so that instead of 85 out of 100, you're getting 5 out of 5. So you're confident that with 100% precision that your results are in fact true. Another classification scoring metric is recall. The goal of recall is to find all the positive predictions. In this case, we're going to find all the exoplanets. So recall is the true positives divided by the true positives plus the false negatives. Okay? Example. Did we find all the exoplanet stars? If that's the goal, recall is what you want. Okay? It's useful to try and find all the exoplanets. Why? Because you're minimizing the false negatives. 100% recall means no false negatives. It didn't mean it doesn't mean that they're all correct. Because you could have predictions. See, it even gets confusing to talk about sometimes. What can we have here? There are 4 situations: true positives, false negatives. This is not taking the false positives into account. Okay? You may have a lot of false positives. Okay? You think they're exoplanets, but they're not. But the key is you're getting all the true positives, right? Okay. And then we have one more that fits this group. It's the F1 score. What is it? It's simply a balance between precision and recall, and it makes it one of the most popular classification scoring metrics. Additionally, there are other classification scoring metrics. There's a lot. Okay, so here's a list from the sklearn documentation. I can tell you that the other one of note, you see this group at the bottom, the ROC_AUC. That's the receiving operating characteristic area under the curve. That's comparable to the F1 score because it's a balance of true positives and false negatives or false positives. And it's a good one. So generally speaking, if you don't know about the balance of your data, F1 and ROC_AUC are your best options. Okay, I'm not going to go into the details of ROC_AUC here, but You can look it up online, and there's some nice visuals. It's a good scoring metric. If your data is balanced, accuracy is fine. If it's not, you can make some adjustments. Happy coding.